Hello and welcome to the InterPlex. In this InterDialogue, I spoke with Ingo Allekotte, Argentinian physicist and the project manager for the Pierre Auger Cosmic Ray Observatory, which is the world's largest cosmic ray observatory, more than 3,000 square kilometers. We spoke in general about the history of cosmic rays, its varying range of energies. The Pierre Auger Observatory detects ultra-high energy cosmic rays that come from outside the galaxy in particular, and the parallels between cosmic ray research and particle physics research. We also delved into multi-messenger astronomy, science advocacy, the social benefits of large collaborative projects like the Pierre Auger Observatory, which includes 18 countries and hundreds of researchers in different disciplines, and also some more personal issues such as the importance of connecting with nature and the help that brings for recharging the mind. Thank you very, very much for being here with me for this InterDialogue.
Yeah, nice to see you, Henrik. Nice to be here too.
Yeah, it's nice to see you again. So let's start out by talking a little bit more generally about cosmic rays, and then we can get into some of your work at the Pierre Auger Observatory. So what are these so-called cosmic messengers? What are some of their astrophysical sources? How do they get here to Earth? Maybe you can just give a bit of an overview of what are cosmic rays.
Okay, cosmic rays are particles that come from outer space and bombard constantly the Earth, coming from different sources. Cosmic rays were discovered in 1912. Essentially, at the time, people knew there was some kind of very penetrating radiation which reached the instruments they had at that time, and this radiation produced discharge of the instruments called electroscopes, and people were wondering where this radiation came from. At the time, it was known that there was radiation coming from radioactive material which you find on Earth. So the first suspicion was, okay, this might be coming from the Earth, from below, or from some material that is around us. And so people thought that if they go up in the air, up into the atmosphere, they might notice that this radiation diminishes instead of increasing. However, experiments done by flying some electroscopes on balloons, this was 1911, 1912. They realized this was Victor Hess who discovered the cosmic rays. He discovered that going up at very high altitude, this radiation increased instead of diminishing, which was sort of surprising. So, okay, the conclusion is this radiation is not coming from Earth, it's coming from outside the Earth. It's coming from somewhere in the sky. So then a quest to find the sources of this radiation started at the time, and I would say it's still ongoing today. More than 100 years, more than 113 years later, we are still looking for the sources of cosmic rays. We understand that some, what we call rather low energy cosmic rays might be coming from the sun or from the stars or from some astrophysical sources which occur in our galaxy. For example, when a star dies, it produces a supernova, which is an explosion of the star, and this explosion produces these particles. But there are cosmic rays of very, very high energy, and this very high energy cosmic rays are still not understood what their origin is, and we are still looking for it. So we are trying to understand, of all the cosmic rays we receive at Earth, which span very many orders of magnitude in energy, the highest energy ones, where do they come from? What produces them? How do they propagate through the cosmos and reach the Earth, or reach our instruments with this very high energy? And trying to understand what's the source of this this cosmic radiation. So perhaps to recap a little bit to your original question, cosmic rays are particles coming from outer space, not light as we normally think about when we think about astronomy. The first thing you think about when you talk astronomy, you say, okay, you have a telescope and you look at the sky, or you just look with your naked eye. And then what you do get is light, which is visible light, right? Nowadays, we have many other means of doing astronomy. We not only look at the light, which is the visible light, but we also look at radio signals, which is also some kind of light. It's photons. We look at ultraviolet light, we look at infrared light, we look at X-rays, and we look at gamma rays. All this is electromagnetic radiation. So it's a form of light with different energy. But we can also look at the sky, not just looking at the light, but looking at particles that are being spit out by some astrophysical phenomena. And that's our interest when we talk about.
So these charged particles, well, they're protons and charged nuclei. So hydrogen up to what other charged nuclei are you able to detect?
That's one of the questions. That's one of the questions. We know that at lower energies, these cosmic rays are mainly protons. So protons means hydrogen atoms without the electron, just the hydrogen nuclei. That's a proton. That's a sort of elementary particle. I mean, which is a proton. It's a composite particle. But I mean, most of the cosmic rays are protons at lower energies, and we are trying to understand what the cosmic rays are at higher energies. And we have indications that we are not only seeing protons, we are also seeing helium nuclei, or we are even seeing much heavier stuff, which is nuclear atoms but stripped off their electrons. So it's just atomic nuclei which are reaching us on Earth with different masses.
Theoretically, is it possible? Sorry, go ahead.
Yeah, with different masses and with different charges. As you mentioned, these cosmic rays are charged particles. Being charged particles allows us to understand that they might be accelerated with electric fields. That's good because then you can explain how they get their energy, but they also get deflected by magnetic fields. So this is a problem because if you have magnetic fields which are between our galaxy and where these cosmic rays are produced, then the cosmic rays, charged particles in the magnetic field, get deviated. So they reach you from, and if you look at the direction from where they are coming, this is not the direction where they were produced because they were deflected on the way here. So that's
part of what makes it so difficult to identify the sources, correct?
Exactly.
Because of the magnetic field.
This makes it difficult, and this makes it a big challenge to understand the sources because you get sort of a blurred images. At very high energy, you expect the deviation to be not too big if they are protons, who has relative little charge. You expect the deviations to be larger if they are heavy nuclei. So one possibility would be if we could identify case by case if a cosmic ray is a proton or something heavier, and just select the light ones and the less charged ones and look at the directions where they come from and infer the possible sources.
Origins. Okay, great. Very interesting. We'll get a bit more into some of the possibilities for detecting the direct sources. I want to ask you about the present and historical kind of interrelationship between cosmic ray astrophysics and high energy particle physics. How do they complement each other? How are they different? I know you're saying there's a large, many different orders of magnitude for the energy of different cosmic rays that are detected. So how do these two fields kind of work together, and how do they separate as well?
Yeah, that's a very interesting question. Just already from the historical perspective, right? in the beginning, physicists last century did not have accelerator, so they had to study elementary particles coming from cosmic rays. So that's, for example, how the positron was discovered, how the muon was discovered, how the pion was discovered. Many elementary particles we know nowadays were discovered through the study of cosmic rays, right? I mean, you had the cosmos, which could accelerate particles, and scientists just caught those particles with detectors. At the time, photographic emulsions were used, and then more sophisticated cloud chambers, bubble chambers, and so on. But so the physicists, according to one of these outreach books, which is very interesting, at the time they were sort of particle hunters, right? They were just trying to catch these particles and understand them from cosmic rays. Okay, then later on, accelerators were built, accelerators with enough accelerating power to bring the particles to very high energies were built, and nowadays we can study particle physics with accelerators. So we look at particles that are produced by mankind, and you can, of course, control this production and control these collisions of particles, which makes it much easier. But we have one of our largest accelerator on Earth is the Large Hadron Collider at CERN, the border between Switzerland and France. And the LHC, the so-called LHC, the Large Hadron Collider, produces particles up to a certain energy, right? And now we have cosmic rays which have energies which are 1 million times more energetic, or even some of them even more, 100 million times more energetic than the ones we can produce at Earth. So this opens up again a new window to study particle interactions at energies which we cannot achieve on Earth. So this is also an interesting perspective. And there are some lines of research along this line which are related to studying these particles of very high energy and doing particle physics with these cosmic rays.
So both have contributed a lot to fundamental physics. Would you say that cosmic ray research has more of a possibility for discovering new physics, maybe beyond the standard model, because you're working at higher energies, or what would you say? Because I mean, that's what they're looking for at the LHC as well.
As physicists, what one always looks for is, of course, new physics, and one tries to look where the model might have cracks or inconsistencies, and there one digs and sees if there you find a problem or you find something new or something unexpected. Of course, this is much more difficult with cosmic rays because of the reasons I just mentioned. It's much easier to have a controlled experiment, to have an accelerator where you just know what's coming in and when it's coming in and how it's coming in, than just looking up into the sky and waiting for something to happen. So you get much more cleaner signals in accelerators, and you get much, your expectations for finding new physics are, I would say, higher in accelerator physics than cosmic rays. But I would not discard it. I mean, there are a lot of astrophysical phenomena which we don't understand, and where eventually we might need new physics to explain. Or at least put boundaries on it, right? Okay, you can say, I have these results which are compatible with what we are seeing in accelerators up to a certain degree. So you cannot drift too far off from those results.
Yeah, it's exciting. A lot of possibilities. So would you say that cosmic ray research sort of functions as a bridge between particle physics and astrophysics, and maybe even cosmology? Is it that research at the end?
I mean, of course, physics is just one, so everything is connected. And yes, sort of, you're looking at the largest scales. the universe and trying to understand not only what happens at the largest scales, but also what happens at the tiniest scales, which is what particle physics does. So it's kind of bridging those two lines of research and sort of making complementary.
Well, in terms of cosmology,
it's a complementary way of looking at things. You need to understand all pieces of your puzzle to have the puzzle complete. So say that's the image.
Well, I know a lot of this is more theoretical, perhaps, but I did want to just ask about cosmic rays and potential role in cosmic evolution. Large-scale structures, galaxy clusters, superclusters, even the cosmic web and filaments. The space in the intergalactic and interstellar medium. What has been, or at least what are people speculating has been the role of cosmic rays in cosmic evolution and the formation of different structures in the universe?
Well, it's different to answer those questions based on the study of cosmic rays as we do. Our interest is on, as I mentioned, on cosmic rays of very high energy. These cosmic rays, we know they are not coming from nearby. They are not coming from within our galaxy, and that we have very strong evidence for that. Basically because the direction from where they are mainly coming is not coincident with the direction of the center of our galaxy. So this points you somewhere outside our galaxy. However, what one expects from theory and from what one knows of particle physics is that these cosmic rays cannot come from very far away, so they cannot come from cosmological distance. So in some sense, being extragalactic is already far away for every normal human being, but it's sort of our cosmic neighborhood where we expect these cosmic rays to come from.
I see. Okay.
So
it's not looking for anything going back.
We can explore. Yeah. It's not like other kind of what we call multi-messenger astronomy, which is based on light, on the different forms of light, on cosmic rays, also on neutrinos, which are particles that really can cross big amounts of space and matter and reach us nevertheless without deviation. So in our field of study in cosmic rays, what we are looking is more like our cosmic neighborhood. Say.
What kind of distances are we talking about? How many light years or parsecs?
We're talking about distances of 100 megaparsecs, which is 100 million. It's of the order of hundreds of millions of light years, which sounds a lot, but for cosmologists, it's not that far away.
Right. I understand. Yeah, I was going to ask you if there was any role in cosmic ray research for going back to any of the primordial sources, but that makes sense because of all the interactions over those large distances. It's very, very hard to detect. But one thing that cosmic ray research is involved in is the search for dark matter. How is that going? How does that work?
Well, the cosmic rays we are looking at, we expect them to be ordinary matter. We expect them to be produced in some astrophysical sources of ordinary matter. So we are also not looking directly at the dark matter question or the dark matter problems.
Is that
matter is of course also a very interesting line of research, and people are really worried and trying to find what dark matter is. But that's not something we explicitly did.
Not okay. Is that research more either theoretical, or is it more about like indirect interactions potentially between cosmic rays and dark matter? I was just wanting to know a little bit about
what this is something you could notice, and you need very high precision experiments for that, which we are not capable of.
Got it. Okay. Well, All right, I'll shift a little bit then. Just ask, how does Earth's atmosphere protect us from cosmic rays? And also, what are some of the potential health risks of cosmic rays for space exploration?
Of course, the atmosphere is a good thing to have above us, else we would be fried by cosmic rays. And
the magnetosphere, right? I would think as well.
Exactly. Yeah. But what happens when cosmic rays and cosmic radiation reaches Earth? It gets absorbed in part by the atmosphere. So we, humans being on the surface of Earth, we are sort of shielded and protected by our atmosphere. What happens when a cosmic ray enters the atmosphere? It collides with the nuclei, with the molecules of the air, and produces what we call a shower of secondary particles. So just from one cosmic ray, one elementary particle, one subatomic particle hitting the upper atmosphere, in that collision, more secondary particles are produced, which still have very high energy, and these secondary particles also again collide with molecules of the air and produce more tertiary or secondary particles, and so on, until you get a full cascade of particles reaching the surface of the Earth, right? So from one cosmic ray, you can get millions and millions of secondary particles reach the Earth, spread over a very large distance. Of course, cosmic radiation has always been here since before humankind. We have had cosmic radiation hitting the Earth since the Earth exists. So it's part of, human development has occurred even though we have this radiation. This radiation, one can think it's might be harmful if in high doses. It's like receiving radioactive, being radiated with radioactive material. In high doses, of course, this is dangerous. At the doses we are having here on Earth, it's what you have as a background and you will never get rid of. So
right.
One positive way of thinking about this is that evolution of life occurred because there were mutations. Mutations were in part produced also by cosmic rays. So if it weren't because of the background radiation we have on Earth, including the cosmic radiation, there wouldn't be mutations and then there wouldn't be evolution. So we are here.
It's very interesting.
Perhaps because of this.
Tying those two together. Yeah. So the atmosphere, helps to protect us, but also allows a certain amount to enter that maybe it's contributed to life's evolution.
This is now going to technical aspect. This is what we use to detect the cosmic rays. It would be very fortunate if we just caught one of these subatomic particles of very high energy. We have to catch one of these. Yeah. It's very difficult to do this in outer space, but as you have the atmosphere, which produces all the shower of secondary particles, you don't have to detect the primary particle, which is coming from outside. You just can detect something at the level of the surface where you detect all these secondary radiation.
Sure, and that's the process at Auger, I know.
Exactly.
The subatomic particle cascade. So that's great. In terms of long distance space travel to Mars or beyond, do you think there's a risk in terms of for astronauts traveling for long periods of time since they don't have the atmosphere to protect them?
There is, and indeed, I think when astronauts were sent to the moon and to outer space in the past, this was not a risk that was really considered at the time, but I think you have to consider it, and it poses severe health risks. And as far as I know, this is one of the big limitations for human space travel, which you have to consider. So you have to have a good shielding of your spaceships to avoid cosmic rays. Perhaps one more technicality is the following: is the fact that most of the cosmic rays are low energy cosmic rays, where you get a lot of them, right? And those are the ones that might be more harmful, not because of their energy, but because of the number, because you get a lot. As you go up in energy, you get less and less. The flux diminishes, the number of cosmic rays diminishes as you go up in energy. And the cosmic rays we look at in Auger, they are very, very high energy. So you get really very few of them. Very few of them.
Right.
Just to think about it is, if you have a surface of 1 kilometer squared, which is 1 kilometer by 1 kilometer, and you would try to catch one cosmic ray of this very, very high energy in this 1 kilometer square, you would have to wait on average. I mean, of course, this is a random process, but on average, you would have to wait between 100 and 1,000 years until you get just one cosmic ray. This very high energy.
Yeah, huge difference. Maybe one thing that can help to illustrate the difference, the phenomena of the aurora borealis, which is produced by the low energy cosmic rays from the sun. Maybe you can explain the difference between that and the kind of ultra high energy cosmic rays that you're detecting in your work.
So when you see the aurora borealis, it has another more popular name, right?
Northern lights.
Northern lights, exactly. When you look at the northern lights, those are cosmic rays which are mostly produced and allowed to penetrate the Earth by the activity of the sun. So the solar activity is what drives those auroras. And those are particles of energies of, say, a couple of giga electron volts. So that's unit of energy. The cosmic rays we are interested in and we are looking at are 10 orders of magnitude above that energy. So those are much more energetic. So 10 orders of magnitude, we are talking about 10 to the 20 electron volt down to 10 to the 18 electron volt. So it's, I would say,
and these are the ones generated by extragalactic sources, high energy events in the universe.
So they are far off from those much more abundant solar or even stellar, produced by normal stars, cosmic rays. What we call low energy. It's still energies comparable to normal accelerators on Earth, right? But for us, those are low energy. Right. We look at
but for you, it's low energy. Exactly. I get it. All right. And just going back, I wanted to also ask about electronics, how those can be affected by either low energy or high energy cosmic rays, either in space or ground-based as well.
Yeah, indeed. Electronics is affected by radiation, and radiation can damage electronics. So you have a chip, which is something which is very compact and concentrated on increasingly small scale. If you have energetic radiation which hits it, it might damage it. So that's why on satellites you have really to have robust electronics, which is sort of more resistant to radiation.
Got it. All right, and these ultra high. Oh, got it. And these ultra high energy cosmic rays that you're detecting, the charged nuclei are being accelerated from their sources at near light speed, from what I understand. How does in the detection, and also, especially in the detection, how does Cherenkov radiation come into play? Is it more when you're observing it in the atmosphere, when it hits the atmosphere? Is it more in the detectors? the water detectors, and we'll get into that, but just what is the role of Cherenkov radiation?
Cherenkov radiation is a form of light which is produced by a charged particle passing through a medium, through a material, which is first the material has to be transparent to that light, else you would not detect it. And the charged particle has to be faster than the speed of light in that medium. We know that speed of light is speed of light in vacuum is a speed you cannot exceed with any material particle, because that's what relativity tells us. However, the speed of light in a medium is lower than the speed of light in vacuum. So you can have a particle that, even going at speed which is lower than the speed of light in vacuum, is faster than the speed of light in that material. And in that case, it produces Cherenkov light. And this Cherenkov light is sort of one can understand it as a sort of a shock wave which is produced in this medium because the medium polarizes accordingly. What we do is we have detectors which are big tanks with water. These water tanks are Cherenkov detectors, in the sense that you have the primary cosmic ray, which produces all this shower of secondary particles in the atmosphere. These particles penetrate our water tanks, and once these particles, which still go at very high speed, nearly the speed of light, vacuum, cross the water, then they produce Cherenkov light in water, and that's what we detect.
Got it. Is it also when it hits the atmosphere? Sorry, is it also when the cosmic ray hits the atmosphere that there's a kind of blue?
Indeed,
and like blue light. Yeah.
Yeah. What we detect mainly is what we call fluorescence light, which is not Cherenkov. Cherenkov is more directed. There are telescopes and observatories which concentrate on looking at Cherenkov light in the atmosphere, which is the same phenomena where a particle goes faster than the speed of light in the air. And these are Cherenkov telescopes. Different projects looking at Cherenkov light. Cherenkov telescope array, for example, is one of these. The Hess Observatory in India, or Magic in Spain. But what we look at is at fluorescence light. Fluorescence light can be understood as all these secondary particles which cross the atmosphere. When they cross the atmosphere, they excite the atoms of molecules of the air, the oxygen and the nitrogen. And when these molecules then de-excite, they produce light isotropically. So you get this fluorescence light along the path of the cosmic ray, the secondary particles of the cosmic ray. And this you can detect with telescopes, which look not at the source, but they look at the atmosphere above the surface, where we have the surface detector. So we have two systems. Now talking specifically about the Auger Observatory, we have two systems of detection. One is the surface detectors, which are the tanks with water producing Cherenkov light, and then you have the telescopes, which look at the atmosphere above those tanks to capture the fluorescence light.
Got it. Is that I was just reading about, is that the hybrid system in terms of detection?
Hybrid in the sense that it's two in one, or two systems, complementary systems, which measure the same thing with two different techniques.
Great. Well, yeah, perfect. Well, let's start to talk about Auger. What are the origins of this project? What was it designed? What kind of questions was it designed to answer? And is it, evolving to answer? And we can start with that. Where did this initiative come from?
It initiated in the 90s, where due to other experiments that were made before, it was clear that cosmic rays of very high energy existed. They were already measured by other experiments. Their source was unknown, so nobody knew really where they were coming from, producing them. And with models, it was very difficult to explain the origin of these cosmic rays. So there was a hope that there might be some new physics, as we discussed just a while ago, the possibility that, well, maybe we're seeing something new which we cannot explain with astrophysical models, with astrophysical scenarios. Maybe it's some sort of strange particle, which is an unexpected particle we've not seen before. And there were two main experiments, one in the United States, in Utah, and one in Japan, which used different techniques. The Japanese used scintillators on the surface of the Earth, which is more similar to our surface detector in some sense. And in the experiment in the US used the fluorescence telescope technique. And they were seeing different things. They were seeing a different spectrum. So one saw that at very high energy there was a sort of suppression of cosmic rays. If you go to very high energies, you don't find all of a sudden any more cosmic rays, whereas the Japanese experiment saw that even at the highest energy, there was still, though low, but there was still a flux of cosmic rays. So this tension, this contradiction between both experiments was there. The fact that it was not known really what these cosmic rays were or are and where they are coming from, this motivated, okay, let's study this in big and do a really big observatory to have high precision and high statistics mainly to study these cosmic rays. And also the idea came up, okay, they are using one technique here, the other technique there. Let's combine both and have both measurement methods in one place. And that's how it was born. So originally it was thought, okay, we need to look also at all the sky, northern hemisphere and southern hemisphere. So to have a complete view of all the sky, you need two observatories, one in the northern hemisphere and one in the southern hemisphere. In the end, we started with the southern hemisphere observatory, and turned out, okay, the northern one might not be as important at this stage, and we just kept the southern observatory, which is
southern one. And when you say it's big, what was it, 3,000 square kilometers? Is that right? The size?
That's
well, it's huge. Yeah.
More or less the size. I mean, it's sort of irregular shaped, and every now and then one of the detectors has an outage and you lose. But
and what is it? Just 1,600 water detectors, something like that.
Sorry, just to make put it in context, 3,000 square kilometers is an area which goes 50 kilometers by 60 kilometers. Right? So 50 kilometers wide, 60 kilometers from north to south, roughly. It's, as I said, it's irregular shape, but that's the size. And on that size, we have 1,660 surface detectors. So between one detector and the neighboring detector, the distance is 1.5 kilometers.
Great. Yep. And what's, maybe to just get into some of the logistics, what's the collaborative structure of such a big project? How many scientists are involved? How many institutes? How many countries?
Yeah, we have.
How is it funded?
I mean, of course, an experiment of this size, of this dimension, you cannot do it just a couple of scientists getting together and going for this. You really need a huge international collaboration. Expertise from very different type, from very different kind. So when this started, first there was the idea, okay, let's do really a big observatory. And then you have to design it. So you get together a couple of experts, 10, 20, 30 experts, which sit together for some time. This happened in a workshop that was held for 6 months at Fermilab, where the design was done. So, okay, let's put this on paper, and what do we want to build, and how do we want to build it, and what's the technology we would use, and what would it cost, and how much time would it take to build something like this, and what are the conditions you need from the site, and so on and so forth. And once you have this design, you start looking for scientists and institutions who are interested in this. Okay, let's go around and see who can participate in this project and who is interested in financing this project. So nowadays we have 17 countries which are participating in the project, which is a good thing, that it's not just dominated by one or two countries. It's really very federal and very well balanced. The participation of the different countries, and all countries are really providing very useful contribution. It's roughly 90 institutions what we have nowadays participating in the project. All of these institutions publicly funded, and roughly 400 scientists. So the expertise is really broad. It goes from electronics to theory and to data analysis, and so you really need a broad amount of expertise to this. And on the side we have some 40 technicians, engineers, and scientists who are present on the observatory site, doing the maintenance and the operations, day-by-day work.
Yeah, wow, huge project, collaborative. Kind of a side point. I'm talking to you from Bogota. I saw that Colombia was an associate member of the project. Is that right?
It's now a full member for some years.
It's a full member. So what's their role? I mean, I know a lot of researchers in Colombia, but nobody in particular involved with Auger. So what is their involvement?
Yeah, Colombia is working essentially on subjects related to the fluorescence detector, and also on a very interesting side project, which, I mean, when you start, now let me drift off a little bit from your question, but when you start with a project of these characteristics, you sometimes have an objective and you want to answer some questions. But while you're doing this, new questions arise and new interests arise. And for example, we noticed that we are able to see with our fluorescence telescopes, which are not pointing at the sources, they are pointing at the atmosphere. We can also study some very interesting atmospheric phenomena, which is some lightning and some electrical discharges which happen very high up in the atmosphere, and which are not very well studied with atmospheric physics and atmospheric sciences, because nobody builds such telescopes looking at the atmosphere. So it turns out, okay, we can understand and see some atmospheric phenomena related to this, to these discharges, and do some research based on that. And Colombia in particular is participating in some of these projects.
Oh, that's fascinating. I remember reading some research a little while ago that there's the possibility that ultra-high energy cosmic rays interact with ice crystals in thunderclouds, and there's this complex interaction that goes on within the clouds. Have you been involved with that research at all, or familiar with it? Atmospheric physics, I suppose.
Not personally, but the Auger Observatory does study also some, as I said, atmospheric phenomena, and there is a lot of new research about the influence of cosmic rays on the development of lightning and storms and discharges in the atmosphere, and also trying to understand when you have discharges in the atmosphere, you have really very high energy potentials, electric potentials, which can accelerate particles at very high speeds, at very high energies in the atmosphere. So these gamma rays produced by electrical discharges are being studied now also with our detectors and with our detection techniques. So this is also a line of research which nobody thought of 20 years ago when we started with the project, and it's now becoming increasingly interesting to do other kind of science.
Sure. That's really exciting how other lines of research emerge from a big science collaboration like this one. So, yeah, that's really cool. And yeah, thanks for explaining about Colombia. I was curious about that. Going back then, why was Argentina selected as the site for this observatory?
As I said, the first question or the first request was to have two observatories, one in the northern hemisphere and one in the southern hemisphere. And you need an area which is very flat because you want communications between the detectors and your antennas. So you do not want to set up too many antennas, so you don't want really to have too many ridges or too many mountains in between. So you need a flat area,
right.
3,000 square kilometers. You need clean atmosphere, clean sky for the fluorescence telescopes. You need so you need also a climate which is favorable, not too many clouds, not too much rain, much wind, and you have to be at a certain latitude. You do not want to be too far south, because then what we do is we use the rotation of the Earth to look at different portions of the sky. So if you are too far south, you really are not making use of the full rotation, and if you're too far north, you don't see the South Pole. So you want to be somewhere at an intermediate latitude, and you want to have a place which is accessible, the 3,000 square kilometers, where you can drive into it with your truck to bring out your detectors and to service the detectors. And you do not want too much human activity there because you do not want to have too much light pollution, but you want to have some infrastructure on the other hand, because you need, technicians and workers need to live somewhere, and you need services to service your truck and so on. So you need a nearby city, but not much population. And if you start looking at places like this in the southern hemisphere, you don't find many. So
So where is it exactly?
So there were sites at the beginning. There were sites selected in Australia, in South Africa, and in Argentina. And within Argentina, we had pre-selected two sites, one in Patagonia. And if you look at the triangle of South America and the south, in the middle of Patagonia, it more or less satisfies this requirement. And the other option was roughly at the mid-height of Argentina towards the west near the Andes in Mendoza, where we finally decided to build the observatory. Convenient.
Great.
I think also the fact that in Argentina there was a scientific community which was interested in the project. There was political support, and it was, I think, at the time rather convenient from the point of view of the costs and the logistics, all of this. And a suitable site where we said, okay, we have sites which satisfy all the requirements. This made the collaboration choose Argentina.
Great. Yeah, and you mentioned political support. I imagine that was at different scales, at local scale and national scale. In Argentina, they were a bit more supportive of science at the time than they might be right now, but they were on board for the building of a project.
We were very lucky at the time. They were supportive, and also they understood the importance of such a large project. So they made a strong commitment to provide funding, not only from the national government, but also from the province and from the Atomic Energy Commission. So they said, okay, 3 institutions, national, federal funding, province funding, and Atomic Energy Commission funding would support the Argentinian part of the project, and that sort of inclined the weight towards selecting Argentina in some sense. Yes.
Great. And more personally, how did you get involved? Like, what was your background before you got involved with Pierre Auger, and how long have you been working there? What's your current role at the observatory?
I did my PhD in physics in Bariloche at the Balseiro Institute, which is an institute of science and engineering. And I did my PhD in theoretical particle physics. So I looked at what we call string theory. And after that, I moved to Europe, to Germany, where I got involved in managing Max Planck Institute, managing the visitors program for Max Planck Institute. And it was a time where institutes were being created in the former East Germany in Germany. So I got involved in the construction and the launching of one Max Planck Institute. I was very young at the time. And so I got some management experience doing that activity over there. But nevertheless, I kept contact with my professors here in Argentina, who were telling me that there was this idea to bring a project, a large-scale project, to Argentina. And when it got started, when we said, okay, your project might be coming to Argentina or is coming to Argentina, I came back. And first I got a fellowship. It was not a position, it was a fellowship because there were no positions available at the time, but nevertheless I decided to take the risk and come and participate in the project. And that was when it was starting, when we were selecting the sites and we were characterizing the sites. So I got involved in the site characterization. We drove out to the field and were looking at the site and looking if the size was okay, if it was accessible, if the atmosphere was good enough, and so on.
When was this?
Sorry?
When? What year was this?
I came back 1997, end of 1997, and beginning of 1998 with all this site surveying. And okay, then came a critical period for the for the project, because that was the time where funding was not secured. Some funding was secured. The people responsible for the project at that time were trying to secure more funding to get started, but we did not have all the funding to get started. So there was 2 years with a little bit of uncertainty. I did some other things during those 2 years, and then in the year 2000, it was decided, okay, let's get started now. Even though we didn't have all the money for the project, we had roughly 50% of what we needed, and people said, okay, let's start, and the money will show up later, or we just build half an observatory, half as big an observatory, and we started at the time. And this was the end of the year 2000. Okay. Since then, I'm involved. I'm sort of involved since the beginning of the project. Since we put out the first detectors in the field, we had prototypes out there, and we're trying to make them work throughout all the construction time too.
Yeah, no, that's really exciting to see the entire process. And what is your current role with the project?
Currently,
has it changed over time?
It changed over time. I was first in charge. I mean, as I got involved at the beginning, the surveying, and was sort of in charge of the site task and the site activities. Then I got involved in the surface detector task. That was task leader for the surface detector, and nowadays I'm project manager of the project. So sort of,
great.
Oversees
a lot of things to manage.
All of the management of it, yes. Far road from theoretical physics to management. It's okay.
Hey, well, as the manager, I'm curious, how is all of this massive amount of data shared between scientists and also with the wider scientific community?
The data itself, is being recorded by the observatory. The observatory surface detector is working 24/7, so it's non-stop, and we're collecting data all the time. All this data is compressed into certain files. It is sort of cleaned and depurated from bad periods and so on, and then this data is shipped, and this means through internet, sent to a data center in Europe, where it is stored and people can access it from there. So all collaborators have access to all the raw data from the beginning.
Okay.
And everybody can do her own analysis. And of course, all the analysis we do is shared among all the collaboration, and is then published in scientific journals as a collaboration paper. Whereas we have internal reviewing processes, and we have internal internal reviewing and internal editing, and make sure that all the collaboration agrees to a publication before it is published. And the
publications are how the results reach the international community. The publications are the main form that the data reaches the international scientific community.
Yeah, exactly. We do also have what we call an open data portal, where anybody can just access the data through this portal. And this is presently 30% of our data, which is available to the general public. So it has some delay of a couple of years. So it's not the most recent data, but it's 5 years back. You can access 30% of all the Auger data, and anybody can analyze it and use it. We use it for teaching purposes, but also some scientists are interested in digging themselves into the real data and making studies with this.
Great. What has Auger discovered to this point? I know you mentioned the identifying the extragalactic origins, which was based on the anisotrophies of the arrival directions. Can you talk about that discovery in a bit more detail? I know it was pretty well publicized. That's a major accomplishment. So how did that come about?
Yeah, what we do is we look at the arrival direction of the cosmic rays at different energies and in different energy bins. And what we see is that at high energies, relatively high energies, within what we can observe, there is a portion of the sky. It's not a direction at a small angular scale. It's at a large angular scale, but sort of you see more cosmic rays coming from one direction than from another one. And the direction from which they come primordially is not the center of our galaxy. It's far away from the center of our galaxy. So this points clearly to an extragalactic origin. And that's one of.
How many detections are we talking about to help confirm that?
Well, this is a lot, because there you really need lots of events to do this what we call dipolar study. So you have really thousands and thousands of events which you can use for this.
Many thousands. I just was asking. That's helped to give really high level of confidence, those many thousands of detections to identify the anisotropy.
So this is really an anisotropy which is already established as existing, and it's beyond uncertainties, both statistical and systematic. So this is just one of the discoveries. The other relevant discovery is related to the spectrum. If you talk about the spectrum, you're talking about how many cosmic rays you see as a function of energy. And we see some structure in the spectrum. We see, for example, that at the very highest energy, you do have this suppression, this cutoff, which was sort of this dilemma between the Japanese and the US-based experiments, where one saw the cutoff and the other one didn't. So we confirmed the existence of the suppression. We also see some additional structure in the spectrum, which might be some phenomena.
Is this the GZR cutoff that you're talking about?
Exactly. It's called the GZK cutoff. So to go into this, when the microwave background radiation was discovered in the 1960s, shortly afterwards, 3 physicists, Greisen, Zeppelin, and Kuzmin, said, okay, if this microwave background radiation exists, then they should interact with the very highest energy cosmic rays, and they should be very much suppressed because of this interaction. So you should really see a cutoff at the highest energy. Nowadays, we understand that the suppression has some relevance for our studies and for what we are seeing. But there might be another effect, and it might simply be that the astrophysical sources at the highest energy, as we say, they run out of steam. At some stage, these sources are not able to accelerate particles to higher energies still. So what we are now seeing, this suppression, is most probably a combination of both effects. It's a GZK cutoff, which is related to propagation, but it's also a source effect where the sources really are not able to give so much energy to the particles. So,
and what is the cutoff energy, approximately?
It's a little bit below 10 to the 20 electron volts. So that's 100. Still pretty energetic.
Yeah,
it's between 10 and 100 million times higher energy than the LHC.
Okay. So this exists for two possible reasons: the interaction with the cosmic microwave background and the limitations of the highest energy sources, potentially.
Exactly. Yeah. And so what we are doing now is we are trying to fit all of our variables together, which is understand the arrival directions and the anisotropy we might see in arrival directions. Understand the evolution of the composition, what kind of particles we see at different energies, and the amount of particles we are getting. So the spectrum, the composition, and the anisotropies all put together, and to have a unified picture. I mean, that's our objective, to have a unified picture of all this, explain all 3 things together: spectrum, arrival directions, and composition, and out of this make a coherent picture of what the sources might be. That's our ultimate goal.
So you would just say those are some of the main present and future objectives for Pierre Auger.
Exactly. That's the main objective nowadays of Auger, to understand all in a combined way. Understand the sources, the propagation, what's producing them and how.
Some pretty major objectives.
Yeah, I'm just saying,
very exciting.
There are a lot of side projects and side questions which are showing up, which we didn't have at the beginning. For example, we see in the showers that we have more muons than what we would expect from theory and simulations. So muons are a very penetrating kind of particle, a charged particle. It's like a muon is like an electron, but with higher mass, roughly 200 times higher mass. Now, these muons are produced in showers, and this is a well-known phenomena, and one knows how these are produced, and they are produced at energies which we can mimic with our accelerator, so it's physics we should be understanding. However, if you look at models, if you look at simulations, you don't get as many muons as you get the showers. That's what we are detecting. Mm-hmm. So there might be some particle physics issue involved, or some parameters we have to tune. And it goes both ways, right? On the one hand, we are providing information to the particle physics people, because we say, look, here's something that is not consistent, and they are doing their measurements for us to make more precise simulations and give us feedback about that. And this is something we still have to resolve. I mean, this immune discrepancy which exists in cosmic rays is something we have to look at in more detail and eventually might understand in the future.
Well, that's that interrelationship we were talking about before.
And
about
it's a
particle
question
physics
that we did not have at the beginning, right? It's a question that appeared now where we have the observatory running.
Yeah, no, it's that's
how
great.
Science works.
As
you get to answer some questions, but new questions show up, and that's the way you progress.
Right, that's what's so exciting. Yeah, you don't know exactly what questions are going to present themselves in a project like this. So I want to talk about multi-messenger astronomy, but before I do that, are there any other research lines that you'd like to emphasize that are being worked on directly at Pierre Auger?
Well, what is presently we can study the composition of the cosmic rays. This means to try to understand what particle is the particle that's coming in from outer space, the primary particle. And presently we can do so in a statistical way, in the sense that we just study a lot of these cosmic rays and see in average what's the mass, or what is the fluctuation of the mass of these particles. And what we are finding is that at the highest energies, they are heavier than what we thought at the beginning. So this is also a challenge and something to understand. And this combined model to put everything together and to see why the models give us, or how can we tune our models to give us these heavier particles at higher energies. That's something we need to understand.
So these are heavier subatomic particles?
Yes.
Is that what you're saying?
So
or heavy nuclei?
I mean, at lower energies we see protons, but if you go up, then you see something like helium or carbon, hydrogen, oxygen, or even might be up to iron nuclei, which we might be seeing at the highest energies. Then when we
have you detected iron nuclei, Auger?
We statistically, what we do see is that they get heavier. We're not sure that we cannot say that it's going up to iron, but it's getting heavier. So there is still a lot of uncertainty, and it's very difficult to really measure precisely the mass of each primary cosmic ray.
Theoretically, is it possible to detect cosmic rays of heavier elements than iron? I know you say that they get diverted much more by the magnetic fields, but is it possible that there are high-energy cosmic rays that are of heavier elements than iron?
You do not expect anything beyond iron, because iron is at the most stable nuclei, and then it gets unstable again. So the thing would disintegrate more faster, and it's also more difficult to produce them. So this would be very, very rare to have something beyond iron. But no, what I wanted to mention is that as we are trying to understand the composition now, what we did recently in the recent years is an upgrade of the observatory to increase the capacity of analyzing the shower of secondary particles. So what we did is, what we did, because we completed this already, the construction, and now we are starting to analyze the data, is to add to each surface detector one scintillator. So to the 1,660 tanks we have out there in the field with this water Cherenkov detectors, on top we put a scintillator, 4 meters square each, and we also have antennas for radio detection. So the shower, when it goes through the atmosphere, produces a radio signal, and this radio signal we can capture with some antennas, dedicated antennas for this. So we look for a radio signal in coincidence with a surface detector. Or we look at of signals in the scintillators in coincidence with the surface detectors. So this is a major upgrade we did. We changed all the electronics. We now have faster electronics in our system. So every surface detector has faster electronics with higher dynamic range. And we also have underground muon detectors, just to understand the muons that are participating in these showers. In a portion of the array, underground means 2.3 meters below the Earth. We put scintillators to measure the muons. I mean, at that depth, you only receive muons. The electromagnetic part gets absorbed before. And so you can measure the muons directly. All this is part of this major effort of upgrading the observatory.
Upgrade the composition. Anything with neutrinos that you try to detect?
Yeah, good question. Indeed, we also try to see neutrinos. Be able to distinguish a neutrino from a cosmic ray in a very horizontal shower. Horizontal means coming from at a large zenith angle. And the neutrino shower would have a particular signature. So we're looking for those two. Perhaps someday we see a neutrino. That would be great. We haven't seen one yet, but we are still looking for it. We're also looking for photons, or at least presently putting bounds to the amount of photons that might be among these very high energy cosmic rays. So we have to distinguishing this. Sure, this too. Yes.
Perfect. Well, this is a pretty great transition into multi-messenger astronomy. Then maybe you can bear with me as I try to unpack this a little bit. I'd like to give a little bit of a focus to neutron star mergers, and I understand that this, as you've explained to me, that some of these more distant high energy events are difficult to detect at Pierre Auger. But when I was studying, I remember learning about some theories, I think was presented by Glenis Farrar. They were saying that neutron star mergers could be one of the primary sources for ultra high energy cosmic rays. And that could explain some of the correlations between energy and electric charge. And then the R process for the production of heavy elements could give a clear signature to the origins of some of these phenomena. So, well, I think you've already answered before that none have been detected with this kind of signature, but has anything been suspected, or are there any attempts at detecting high energy cosmic rays that might be coming from neutron star mergers?
Yes, I mean, this is part of our quest to understand the origin of these cosmic rays and to understand really what the sources are. We have different candidate sources. We have different models, which are valid models and which are interesting models and provide possible sources. What we do need is to gain enough statistics and to gain enough events cosmic rays from which we are collecting to really make a precise statement about what their origin is. We are not there yet. We have both from theoretical point of view and also experimental hints we are receiving some candidate sources, but we cannot at present say yet what is
confirmed. Theoretically, do you think that's a probable or possible source of ultra high energy?
And it's being considered seriously, yes, of course.
And does that establish, if that's true, kind of a fundamental link between the production of ultra high energy cosmic rays and gravitational waves as well?
Well, that would be, of course, would be interesting to see, although the correlation of that is very difficult to assess. Because cosmic rays, as they get deviated in magnetic fields, as we said, they propagate. They have to make a longer path, and this means that we get them very much delayed. So you will not see temporal coincidences between those. That makes it difficult.
Right. Yeah, I was going to ask about that. I think, as I mentioned to you, I had a nice conversation with your compatriot physicist, Jorge Pulin, who works with LIGO now. And we spoke about gravitational waves. Also on the InterPlex platform, we've republished an excerpt from his book with his wife, Gabriela, The Sound of the Cosmos, the Multi-Messenger Astronomy and the Birth of Gravitational Waves and the Birth of Multi-Messenger Astronomy. And that chapter focuses on the 2017 event that detected the merger of neutron stars and the clear signature through other electromagnetic observatories detections of the production of heavy elements like gold. So I wanted to ask if that particular event or subsequent events, Pierre Auger was involved in attempting to see if there were any following signatures of that event, because it takes longer for the cosmic rays to reach the Earth.
Yeah, exactly.
Was there a collaboration going on?
The problem there is a time correlation which you cannot make between cosmic rays and those events, because it just takes hundreds of years more for a cosmic ray to come from that. Of course, if we would be able to detect neutrinos, and then we could make a statement, because neutrinos, yes, would travel on a straight line, would not get deflected.
Right.
Yeah. I mean, of
right.
course,
So
we are attentive to this, and also there is a multi-messenger. There are networks where there are alerts given, and people look in certain directions at certain times to see if they see something. This is a very interesting approach to combine the different observatories you have worldwide to be attentive with phenomena you might see.
No, absolutely. No, it's fascinating and really exciting, kind of taking a bird's eye view of the whole process of these forms of observation coming together. I mean, these neutron-star mergers are also a strong candidate for short gamma ray bursts. And there seems to be a lot of correlation between ultra-high energy cosmic rays and gamma rays, both from cosmic origins and also in the subatomic particle cascade. So I don't know. I guess my question is how do cosmic rays and gamma rays work together as well?
Yeah, I mean, it's all this multi-messenger approach where you really want to have a consistent picture of what's going on. So if we identify sources or if we see the cosmic rays of the very highest energies, you expect to see gamma rays and neutrinos at somewhat lower energies. And this has to be all compatible and has to make just one complete picture of the whole, right? So the flux of gamma ray has to be consistent with the flux of cosmic rays at higher energies, and flux of neutrinos at lower energies has also to be consistent with the flux of cosmic rays at higher energies.
So, I was just saying, to clarify a little bit, these other forms of detection, whether electromagnetic, the wide spectrum of that, neutrinos, gravitational waves, they take a much more direct path to our instruments, our observatories, as opposed to cosmic rays. So could these efforts of multi-messenger astronomy help in identifying the sources of cosmic rays, since those ones actually, if you're able to see a clear signature?
Yeah, of course. And this is an interesting path, and you have seen that the gamma ray astronomy has made much progress in more recent times. And for example, detecting sources of gamma rays in our galaxy gives you some hint about acceleration mechanisms of cosmic rays of lower energies than what we are looking at, but nevertheless of quite high energy cosmic ray processes which happen in our galaxy. And I think the same might happen if one collects sufficient statistics and gets to collect sufficient data to understand also extragalactic processes.
Great. Yeah, I tried to it helps for me to illustrate, and I think for other people, just thinking of the neutron star mergers as this kind of nexus of fundamental forces and processes that include basically all of the different elements that we're talking about, and how that could be used in helping to identify sources and origins of ultra-high energy cosmic rays. So just wanted to get your thoughts on where you see that going in the future. And I know the distances, and when you say now there's hundreds of years of delay in detecting a high energy cosmic ray from one of these events as opposed to a gravitational wave, but how do you see, what would be the most realistic possibility for sources, other kinds of sources perhaps, or is it maybe active galactic nuclei or some other potential ones that you see as a method for multi-messenger astronomy that could include cosmic ray?
What we see as possible candidates are active galactic nuclei or starburst galaxies, galaxies that have a very high star formation rate. As said, what we expect to see is things that are outside our galaxy but not too far away. So that's, I think, our target of what we're looking at, because we expect our cosmic rays to come from things that are more or less nearby, to sort of
supernova as well. Supernova explosions.
Supernova explosions, the energy would not be enough to reach those high energies.
Not high enough.
Okay. We don't expect supernovas to be the origin of the ultra highest energy cosmic ray. As I said, those are more extragalactic phenomena. Should be happening near black holes or near very, very more violent and more energetic phenomena.
So are there some candidate sources for active galactic nuclei that you're targeting?
There are, and there is a full catalog of sources of active galactic nuclei. Centaurus A is, for example, one of them, and other possible sources which are not very far off from Centaurus A, which might be possible sources. We have already in the past pinpointed them as possible candidates.
Well, I want to also ask you about the space observatories, space cosmic ray observatories, how they differ from something like a ground-based Pierre Auger Observatory. These are more based on like advanced direct detectors.
Exactly.
Is that right?
And
directly
space,
detecting
what you can have in space is a detector which receives the primary cosmic rays and detects the primary cosmic ray. And this is interesting and useful at lower energies where you have a higher flux of cosmic rays. So you can really catch the primary cosmic ray. The cosmic rays we are looking at, where you have 1 per kilometer squared per century, per millennium indeed, you would not expect to catch one of those on a satellite unless you build a satellite which is thousands of kilometers square big. So
I guess there's no plans for that.
There's no plans for that, but there are plans, and there are projects which propose to have telescopes on the satellites looking at the atmosphere. And as we do our fluorescence technique in the atmosphere, looking at it from Earth, you could look at it from a satellite, which a much broader area you're covering. So
I see.
That is something that is being proposed and thought of, having fluorescence telescope on board of satellites to look at the showers.
That's interesting.
So
what was it, the alpha?
This would allow you to increase a lot the area you're watching, and therefore increasing the statistics at the highest energies. Our main problem is the statistics you are getting. How many events do you do?
So the alpha magnetic spectrometer, the one that was on the International Space Station, that was only detecting low energy cosmic rays?
Exactly.
Right. Was that giving interesting data, though, or that's very separate from the work that you do?
It's, of course, interesting data. It's a phenomena different from the one that we're looking at, but it gives you also... because they can measure very precisely the flux at much lower energies, of course, and they can also make many statements about composition of cosmic rays. So lower energies. So, again, as said, this helps make complete the puzzle somehow, right? So you get some pieces at the other end of the puzzle, but nevertheless, it's the same puzzle.
Definitely. Well, you mentioned gamma rays. When we first met in 2013, I think you were still involved with the Cherenkov telescope array. Can you maybe give some idea what's happened or why you decided not to participate in that anymore?
Well, it was decided to site the CTA in Chile and not in Argentina, so our participation would have become more difficult. I would say at the time not feasible. So we were
sure.
We participated at the beginning. We participated in the site selection and tried to have CTA come to Argentina too, which didn't happen. So they are now planning to build it in Chile.
Sure. And is there any agreement for sharing data or doing multi-messenger astronomy in some way between the two
not with
projects?
Not with CTA at present. We do not have a collaboration. I mean they're still in a preliminary phase.
Right.
We might be testing one CTA like telescope in the future, but this is just as a side project. A few of us are involved in.
Great. All right. And I have a few kind of general questions related to Pierre Auger also that I'd like to kind of just, you've mentioned it. Are there any deliberate kind of interdisciplinary research projects that are being developed there beyond just particle physics and astrophysics? Are there kind of ways of correlating these various lines of research that are emerging with some of the other disciplines that were maybe the main objectives? Are they working together? Is it mostly separate?
Well, Auger, what it does have is a facility where we have some infrastructure, we have trained technicians, we know how to move around. So we have been giving some support to some earth science projects like an array of seismographs that have been established and installed in the field. And this is something completely different from Auger, and it's not part of the observatory, of course. But we have provided some support for some seismological study projects, for example. There is some project going on for studying aerosols and tiny particles in the atmosphere and the propagation of tiny particles in the atmosphere, where again we can provide some support to doing this and measuring this. We have been trying out different prototypes for detection of cosmic rays in the radio regime at very high frequencies, in the gigahertz regime. We have installed some instruments and some prototypes for measuring this too. It was not part of the main objective of Auger at the beginning. So we participated there too. We are now seeing the laser shots from LiDARs on board satellites, which is also a very interesting sort of side project in the sense that these satellites do atmospheric studies and do characterization of the atmosphere. And we see the laser shots they are shooting down to Earth. So we saw events very periodically coming in a very straight line, which beginning was a little bit strange, but then it turned out that these were shots from a satellite. And so we are able to intercalibrate instruments. We calibrate our telescopes with their laser and help them calibrate the laser with our telescopes. So this is also an interesting side effect of the project, right? So participating in some space-based projects.
Definitely.
Then additionally,
fascinating. Yeah, so many different things.
The fact that we had the infrastructure of Auger there in place allowed us to install some calibration, some reflector cones for some satellites that use these reflectors to calibrate their images to, both in intensity and in coordinate. Yeah, to fix their positioning of their satellite. I mean, this was support given to the Argentinian Commission for Space Activities.
Well, yeah, so many different extending lines of research and collaboration. Yeah. It's exciting. I'd like to speak a little bit about maybe more of the social or the socio-scientific impact of a project like this. I think I'll start with a bit more of a kind of broad question, if you don't mind.
Yeah.
Especially given the current state of the world. How do you see a project like this, and also multi-messenger astronomy that tries to address sort of more foundational questions, that brings together many different countries and researchers? How does that help to build like a common understanding and maybe address some of the anti-scientific sentiments that the world is experiencing now? How does it help to kind of bring a bit more excitement towards science and build a common understanding around foundational questions? I know it's a sort of expansive question, but what are your thoughts?
Lots of thoughts about this. I mean, indeed, I think doing science in a collaborative way with people from different countries, as you mentioned, it helps very much to bring down barriers and prejudices. It really helps understand, of course, at the scientific level, but also the human level. You get to form a network of collaborators who are distributed among many countries in the world. I think it's a very valuable contribution to science diplomacy, which is many times underestimated as something that has a global impact, and the ability to talk to each other, even though there might be idiomatic barriers or might be differences. So this, of course, is useful and necessary. On the other hand, you have technological development, right? These kind of scientific projects are always accompanied by some technological developments, and this means not only the electronics and the software and the data handling, it's also about hardware and about creating capacity to build a detector of this kind, which requires companies to provide a certain standard of quality, which you do not always have. So participating in constructing a project like this contributes to developing technology industry and services and service industry too. Yeah. So it's
sure. Well, for the local economy, of course, was in Malargüe.
Of course, and then the third leg is the formation of human resources. Right, you get students who get involved in the project, who learn from the project, and eventually do their master's, their PhD, and then move on to other fields of science or to technology or to industry or whatever. But they are already got nurtured from this big international collaboration to spread somehow this knowledge to other areas of society.
So you have graduate students and postdoc researchers and young researchers that are working at this project as well.
Yes.
That are helping in the
lots of them. And it's an important part, right? The project, I think, one of the objectives, although it's not the science objective, is to really form young scientists and instructing scientists in science. You need this.
Great. Very important. Well, speaking of this important intersection between science and society, you should mention your wife, Karen Hallberg, right? She was distinguished with an award from UNESCO as for women in science, and as you also recently mentioned to me, was named the Secretary General of the Pugwash conferences.
Right.
So I was reading about that after you mentioned it to me. Very interesting. This using evidence-based dialogue for addressing some of the most complex dangers that face humanity. So, well, first of all, I'd love to speak to her at some point. Really fascinating the work she does. But I'd also like to ask you a bit more what do you think of the importance of science and science advocacy and development, diplomacy, as you mentioned, towards addressing complex social and environmental issues? What are some of your thoughts, and also from her?
Yeah, this is something we as humanity have to learn to base our decision making on rational thinking and on data, right? So this is the kind of input science can give to society, to how the scientific method works and how you really use data to make decisions and to move forward. So that is a very important part. And of course, you have to bring it then to the right place, to bring it to the lawmakers and the decision makers, that they really base their decisions on the laws of science, which
absolutely.
Contrary to what one would think, it's becoming more and more complex and difficult in these times, which is sort of strange.
Yeah. Argentina is a case study of that, right? When we first met in 2013, it was more of a kind of a golden age for Argentinian science. There was a lot more investment, but now you're having many projects cut by the current situation. They're not appreciating anything that you're talking about, as I understand.
And I would say it's not only about funding, it's also about the perception of the relevance of science and the importance of doing science.
Right.
And
the wider public too.
That's something that might be missing now, is the understanding that science is not just, as you mentioned just a while ago, it's not just about knowing exactly where the highest energy cosmic rays come from. It's rather about building an environment and having ties to the society between scientists and the society that really promotes exchange, promotes cultural exchanges. For example, the observatory has had large impact in the town of Malargüe, which is a rather small town, 25,000 inhabitants. And I think the cultural impact of the observatory on Malargüe, the fact that the people of Malargüe get to know foreigners who come to work at the observatory, and the other way around, the scientists that come to Malargüe and get to learn the local culture, the local customs, and bring this culture back to their homes and to their countries will be a very important exchange, which is very difficult to measure and it's very difficult to quantify sometimes, but it's there.
Certainly. Yeah, it's true.
The other aspect which is important to emphasize is we have a visitor center where people come and learn what we do, and learn about science, about the interest scientists have in things related to the cosmos and to the space, but it motivates young people to get involved in science, to do science or do engineering, and get interested in technology. And that's also a very important side product, I think, to just motivate. I mean, in a country like Argentina, we need more people in technology, we need more people in science, we need more people who really work hands-on. on concrete problems.
Absolutely.
It's a way of motivating people to get into these areas of knowledge somehow. If you have something that shows
No
that
question.
it's possible.
Well, considering
If you show them that it's possible to do something like this in our country, then people say.
in inspiration, no?
Yeah.
Well, a little bit of a personal question then. I mean, considering all the great work you and your wife do with science and science advocacy, do you have children that are involved in science at all?
I have two children, a daughter who is a physician, medical doctor, and she is working in Bariloche as a medical doctor, gynecologist, and I have a son who is working at Google in Switzerland.
Exciting. Well, data science engineering, so definitely taking after.
Engineer.
And your wife is also your wife is also a researcher in what, quantum information? Is that right?
She is a researcher in solid state physics. Yes.
Solid state. Exciting. Well, great. I know you have to go. Before you do, just want to ask about one other major passion of yours, which I'm sure helps you to navigate all of these responsibilities and uncertainties, and that's kayaking.
Oh yes.
You live in beautiful Patagonia. I know that you go out under any possible weather condition into the mountain lakes with your kayak.
Right.
So
very nice lake.
Yeah. What do you love about it?
I would say everything. It's a nice entertainment. It's a way of doing a little bit of sports. It's a way of connecting to nature. Mainly, we have very nice lakes here in the surrounding in Bariloche and all of Patagonia. And yeah, when you have the chance of going out to the lake, perhaps on a rainy day, on a cloudy day, on a windy day, and you have the lake all for your own, it's a very nice feeling to be out there. Really.
Absolutely. No, I understand very well.
Disconnect from the computer and disconnect from work and worries, as you say, and being out there in nature, just in contact with the water and with friends, because it's also interesting to do the activity with friends and colleagues. This is a big part of it too. After kayaking, we always have some tea and biscuits and have some interesting chats too. So this also.
I'm sure. Do you feel that disconnecting and connecting with nature, as you said, beyond the personal and the mental health aspect of it, do you think it helps to recharge your mind, to be able to work better, to enjoy your work more?
Oh yes, of course. You need some time of being on your own or being in another environment to realize what life is about, that it's not just the work you're doing. There's other things out there, and that's very important, of course.
Absolutely. Is that part of the reason you decided to live in Bariloche, which is an incredibly beautiful place?
It's very beautiful. We have the lake, we have the mountains, we have nature around. So even a hike in the mountains, it's something which does the same as kayaking, essentially. Just get other kind of connections.
Yeah, we all have our activities that we love in nature, so that's great. Well, thank you, Ingo. I know you have to get going to the Institute Balseiro, and it's been really a pleasure talking with you.
Yeah, thank you.
Thank you, and for all the work you do as well.
For your interview, it's very nice. Keep in touch.
I enjoyed it very much. Thank you for joining us for this InterDialogue. You can subscribe to be notified of future episodes and by following us on our social media channels at the InterPlex. Visit our website, interplex.org, for more interdisciplinary and intercultural content and to join our growing collaborative community.